Okay, I had L'Hopital's rule, and it is used to evaluate the indeterminate forms of limits. It states that for indeterminate forms where the limits tend to 0 over 0, or infinity minus infinity, or positive infinity over positive infinity, or negative over negative infinity, or etc., that the limit of that form equals the limit of the form of its derivatives. This takes an indeterminate form to a determinate form, allowing the original to be evaluated. The statement goes to say that when using a limit of x to c of f of x over g of x, if the limit of x to c of f of x equals 0, and the limit of x to c over g of x equals 0, then and the limit of x to c of f prime of x over g of x equals L, which is not indeterminate, then the limit of x to c of f of x over g of x also equals L. And this is also true when, instead of equaling 0, these equal positive or negative infinity. Our first example of this is going to be the limit of x to 0 of sine x over x, which when you plug in x to 0, when you plug in 0 to the top, you would get sine of 0. When you plug in 0 to the bottom, you would get 0, which would equal 0 over 0 because the sine of 0 is 0. So using L'Hopital's rule, we are going to take the derivative of the top, which is sine x. So we're going to take the derivative, which is cosine x. Then we're going to take the derivative of the bottom, which equals 1. Then we're going to send both of these to 0. So then we would get the cosine of 0 over 1, which the cosine of 0 equals 1, and the bottom is 1. So then we got that x to 0 of sine of x over x will equal 1. Okay, so our second example is going to be the limit of x going to 1 of the natural log of x over x squared minus 1. So we're going to plug in 1 to get the natural log of 1 over 1 squared minus 1. We know that the natural log of 1 is 0, and we know that 1 squared, which is 1, minus 1 is going to be 0. So now we're going to apply L'Hopital's rule. We're going to take the derivative of the top of natural log of x, which gives you 1 over x. And then we're going to take the derivative of the bottom, which is x squared, so we're going to move the squared down to be 2x. And then because negative 1 is a constant, we're going to ignore that. So then we're going to take this and move this to 1. So then we're going to plug 1 in, we're going to get 1 over 2. So then from there, we know that 1 over 1 is 1, over 2 is 1/2. So the limit of x to 1 of natural log of x over x squared minus 1 is 1/2 because of L'Hopital's rule. Okay, so our last example is going to be a limit of x going to infinity. We have the top of x squared minus 9x plus 4 over 3x squared plus 7x plus 8. So we're going to send this to infinity, and we're going to get infinity squared minus 9 times infinity plus 4 over 3 times infinity squared plus 7 times infinity plus 8, which when you simplify you get infinity over infinity. And then from there we're going to apply L'Hopital's rule. We're going to take the derivative of the top, which is x squared minus 9x plus 4, which will give us 2x minus 9. Then we're going to take the derivative of the bottom, and we're going to get 3x squared plus 7x plus 8. So we do the square multiplied by the 3, we get 6x. Then we're going to take the 7 plus 7. Then we're going to send this to infinity. And again, we're going to get 2 times infinity minus 9 over 6 times infinity plus 7. So then from this we get infinity over infinity again. So now we have to apply L'Hopital's again. And so we take the derivative of 2x minus 9 over 6x plus 7. We're going to take the derivative of the top, which is 2, and the derivative of the bottom, which is 6. And you can't, because there are no variables, you can't apply the infinity. So that is your final answer, but we can simplify 2 over 6 to 1/3. So the limit of x going to infinity of x squared minus 9x plus 4 over 3x squared plus 7x plus 8 is 1/3.